Hello everyone, good morning. First of all, I'm Eliott. This is my first time at the Flight Software Workshop, and I'm really glad to be here today. I'm a flight software engineer at CNES. I work mainly on IDFX flight software, which will be today's subject, but I'm also involved in overseeing flight software development by interns for a CubeSat mission, where everything is made by interns, from flight software to attitude control algorithm. So it's also a very interesting topics. So first of all, I will present the IDFX rover inside the scope of the JAXA MMX mission. And we will see a bit about the flight software architecture in the frame of the Cosmos development kit that is being developed at CNES. And we'll see a bit about the development process also. So the MMX mission aims at studying Phobos, the largest planetary satellite of Mars. It will launch in 2026 and will orbit Phobos for 3 years, where it will make a remote sensing of the surface and also plan to do a sample return from the surface of Phobos. The IDFX rover is a very small rover, as you can see, maybe the size of a big microwave, and it will be jettisoned from the spacecraft on the surface of Phobos in a Stoke position, and it will then need to upright and deploy itself autonomously. We will not be able to know in which one of the phase we will launch, so everything will be autonomous with a specific sequence. And then the rover will be operated during around 3 months to perform its technical and scientific objective. So the IDFX mission is made in collaboration with the DLR, the German Space Agency. And we have several instruments. We have the navigation camera. I will talk about it a bit later. And we have wheel cameras that are directly pointing at the wheel to do some wheel and regolith interaction. We will study the physical homogeneity and diversity of the area around the sampling site of the spacecraft, and this will increase the value of the MMX sample in a geological context. And something that I forgot to say is the objective of the MMX spacecraft. It is to answer one of a few questions: the origin of Phobos. Is it an asteroid that was captured by Mars, or is it an accretion of matter due to a big impact? On the MMX rover, we also have a spectrometer and a radiometer. This instrument will be complementary to the ones that are on the MMX spacecraft and will perform surface measurement. One technical challenge is the ability to drive in milligravity. So the wheel will turn in order to make the wheel and a regolith interaction, but it is also the mean for the rover to drive on Phobos. And being able to drive around the landing site will give very precious information for the MX spacecraft prior to landing. That's it. And we also have the autonomous navigation. So it is a technological demonstration, but it is also a need, because if there will not be 100% coverage of Earth visibility between the rover and the Earth. So if we are not able to have autonomous navigation, we will not be able to drive very far away from the landing site. And also the visibility of the rover is pretty small. I think due to the small height of the rover, it is around 1 meter. So the objective of the IDFX rover is to act as a scout for the MMX mission and to give various information to complement the scientific measurement made by the spacecraft. So as I said, it is a collaboration between CNES and DLR. DLR is mainly focused on giving us the racks and mini-rad spectrometer and radiometer instrument, and also working on the wheel and the locomotion part, as well as the frame of the rover, while CNES is more focused on the avionics part inside the service module. So for the flight software part, it is also a shared work between CNES and DLR, but CNES is the final integrator for all of the partitions that is developed by the DLR to manage the instrument and the locomotion. So the flight software architecture is based on the Cosmos development kit that is developed at CNES. It is a set of generic partitions that run on top of Stratum hypervisor, the commercial version that is made by Fentis. So the generic partition offer basics software features that are required aside from the payload partition and the platform partition. So the generic partition included in the frame of the Cosmos software is the one in the middle, IO server, input-output server. That is a generic code on for each mission. You only have to describe the input-output and output interface and develop, of course, your driver. We have also hardware and software event monitoring partition that monitors the different events, and also have a scrubbing function to read the DDR memory and to activate the controller for the fault memory fault detection. And we have the memory management partition that manage all the access to the different partition on the onboard computer, and also monitor the state of the partition at startup and for shutdown. We have the CCW partition, which is a generic on a specific partition, because this partition deploys libpus library with generic pus services, and then you can add your own specific services related to your mission. And we also provide a development kit for bare metal or with different type of real-time OS. We are currently working with Lithos OS that is developed by Fentis also, and with AirTems, and we are trying to embed Linux version inside the partition. And so you can see you can develop partition for the payload, but as well as for the platform. All of the generic partition are qualified at B level, and it's flight proven in a variety of French mission. So here we can find the static architecture of the IDFX rover. We have the Cosmos generic partition, HSEM, MMDL, and we have two input-output server, one to access the different cameras, the wheel camera and the navigation camera, and one for the TMTC link. So as we can see, the locomotion partition as well as racks and mini-rad partition are developed by DLR and are integrated inside the software by CNES. And we have two autonomous navigation partitions that are running on a dedicated core. Only one partition is running at the time. It's at startup that we can choose which one of the partition we want to load at startup, and then the partition will have 100% of a specific CPU to run. So we plan to try to run both partition during the 3 months operation. So the test and validation was also shared with DLR. Everything related to their partition was validated on their side, and then the integration test and validation test was done on the onboard computer and also at partition level on simulator that is called the Storm, which is the onboard computer connected to all the equipment running on a simulator. And then the flight software is handed to the command and control team that is responsible for more complex validation scenarios that can be run on Storm, but also on a flat rover. So the integration test environment. So the partition under test is alone on the CPU with another specific partition that only exists for the test in the test environment, which is called the sandbox partition. With the sandbox partition, sorry, we can trigger a set of input in the partition under test, and then verify that the outputs that we are waiting are correctly generated. So everything is scripted for the input triggering as well as checking the output of the partition. So this way we have continuous integration for all of our integration tests of the partition that is under test. So this is a validation of your environment, which we call the Storm. All of the equipment are running on are virtualized and running on a computer. We also have an environment simulation for the locomotion part, because one of the most critical aspect of the rover life will be the uprighting. And to validate this part, there is a specific simulator that simulates the Phobos environment, and we can validate the locomotion command. So for the integration process, when the DLR requests an interface change for one of its partition, the interface change is reviewed by CNES. It is then applied on the full software that is currently being developed. We don't do a specific release because it is still for testing. So the interface change are applied in the full software. We then deliver the new binaries to DLR with the interface change updated. So this way, DLR engineer can test that the new version of their partition is working well with the new interface, and then they will deliver to us their new partition binaries, and we will only run really small tests that trigger the most basic function to validate from our sides, and then we can make a full delivery with the new partition updated. So about mixed criticality. So as I mentioned, the generic partition are qualified at a B level, but all of the non-critical partition, which are the racks, mini-rad, and the navigation partition, are deemed not critical because it cannot endanger the spacecraft and are not critical for its survivability. And all of these partitions are qualified according a CSS C standard. So one thing that I want to highlight is that even if TSP guarantees isolation between the partition, the FDR should be set accordingly to the criticality, because you could end up in a scenario where, for example, you have a failure in a racks partition. If an FDR is set that could make the software, the full software reset, then you could end up in an endless loop of reset because of this. So to conclude about some of the successes and difficulties that we went through, first, IDFX will be the first rover to be developed by the French Space Agency. It is also the first international collaboration based on the Cosmos flight software, and this is a pretty big success from our side. It was also the first flight software that we developed according to agile development technique. And it was a smooth international cooperation with DLR inside a single SOC. So we have all the platform partition and payload partition working inside a single SOC. And one thing I want to highlight is about continuous integration. Of course, it is a very, very powerful tool, but you should not underestimate the amount of time that is required to set it up at first, and then that is continuously required to maintain the test. And it was a bit hard at the beginning to find the right amount of time between looking at the test on a daily basis and only looking at the test result prior to a delivery. And we found something like trying to put a bit of effort every month to have all of our tests going okay, to be something that work for us. So I would like to thank you all for your attention. If you have any question.
All right, thank you very much. We'll take some questions from the room.
Thank you for the presentation. I have a question like when you do the integration, for example, do DLR need the whole image from CNES to do the integration, or they just get some stuff? Like, for example, if you have some French export control on your partition, how does this work?
No, it was a full delivery of all the CNES partition to DLR. All the binary were delivered to us, and then they could just swap their own binaries to test a new version of it.
And another question, if, for example, DLR want to reboot or upload their partition, do we need to reboot the whole system, or we just reboot one partition?
This is no. We are going to reboot the whole system. We have three different versions of the software in non-volatile memory, and we can decide at startup which one we want to start. So what we are going to do is upload a new version of a partition on one of this version, try to start up with the new partition, and if it fails, we can always go back to an old version of the software with the old partition.
All right, any other questions in the room?
I had a quick question regarding, I guess, so you were using the Zinc 7000 series, so those have FPGA fabric as well. And I was wondering how, with the hypervisor, like interacting with like AXI or like DMAs kind of work in that sense. And like, how do you ensure that like your partitions are only accessing memory that's related to that partition and not overlapping and stuff like that?
This is managed at the, we have configured, we have hypervisor configuration that will allow the different partition access, and we have a specific memory that are dedicated to communicate with the FPGA, and this is a hypervisor that control the memory access between this specific area, and that ensures that only the partitions that are authorized can communicate with this part of the FPGA.
All right, we got one more in the room here.
Hello. Do you have any clue of the overhead in terms of resources of using this kind of system? I mean, an hypervisor?
I can't give you a specific number, but yes, of course, there is a big overhead, and in particular, it really depends on the number of partition on the periodic cycles that you are going to use. Our major frame is 1 second, and the minimal frame, some of the partition are running at 10 Hertz, but it really depends of how much partition at running at 10 Hertz. For example, if you have a really slow period inside your major frame, then the overhead will not be too much. But if you have a lot of partition that are running much quicker than the major frame, of course, the overhead will be a lot bigger.
All right, and we'll take one last one from Slack here. Caroline asks, do you know if Cosmos is CCSES compliant? Are there any open source initiatives for Cosmos?
So we are working at CNES about this. So right now, what you need is a license for the hypervisor and a license for Cosmos for the generic partition as well as for the development kit. It is not free to use, but it's I can say it's really, really cheap, and it can be used for any international program. There is nothing related to this.
Thank you very much.